If we want to know the effect of concentration on the rate of a reaction, then we're going to need to derive the rate law. Maybe you remember from Chem 361, or at least from Chem 132, that the rate law is an equation that relates the concentration of the reactants to the rate of the reaction. And so we can write the rate law for a mechanism that we think might be operating, and we can compare that to the rate law that we get based on experiments. So if we start with the associative mechanism, we're going to write the rate law by considering which step is the slowest, the rate determining step. In this mechanism, this first step, the formation of the 7-coordinate intermediate, is usually the slow step. We can also think about the microscopic rate constants, the rate constant for each step. We're going to call the first step forward rate constant K1, and the first step reverse constant K-1, and then the second step we'll call K2. So if we're going to write the rate law, we're going to base that on the slow step. So in this case, the rate of the slow step, and therefore the rate of the reaction, equals K1, that microscopic rate constant for the first step, times the concentration of the reactants. And so concentration of the two reactants. Now, the rate of the reaction is slowed down, so minus sign, by the reverse reaction, K minus 1 times that in the 7-coordinate intermediate, K ml5xy. Okay, now in a rate law, we really only want the concentrations of the reactants because we can't really control the concentration of the intermediate ml5xy. So we're going to rearrange our rate law in order to get rid of the influence of that second term. And the way that we're going to do that is we're going to make the steady state approximation. And the steady state approximation tells us, or what we're saying, is that the concentration of ml5xy is a constant throughout the whole reaction. So basically, like, we make some and it is consumed as fast as it's made. And so the way that that works out mathematically is that so if we think about the rate of the formation of that intermediate, so which will equal K1 times ml5x times y, so that's going to be forming that intermediate, and the rates of the ways that it can be consumed, so the reverse of the first step, and the second step, so here these are negative signs because these are being consumed, K2 times ml5xy, where it reacts, that all of that is going to equal to 0, so that the rate of change of ml5xy is going to be constant. Okay, the concentration is a steady state because its rate is not changing. So if we do some algebra and rearrange this equation so that we can get the intermediate by itself, ml5xy, we see that the concentration of the 7-coordinate intermediate equals K1 times ml5x times concentration of y divided by K-1 plus K2. Okay, so we can put this whole thing back into our first equation where we can substitute for ml5xy. And so if we do that, then we see that the rate will equal K1 times K2 times ml5x times y divided by K-1 plus K2. Now, so we've got all of these little individual Ks, but those are not necessarily things that we can measure experimentally. If we were to measure experimentally the effect of the rate on concentration, we would get some value K, we're going to call K observed, that is the combination of all of those smaller Ks times the concentration of the starting complex and the concentration of the incoming ligand. So what we see is that for an associative mechanism, that the overall reaction order is 2, that this reaction is second order, It also tells us that the rate will depend in a first order way on both the concentration of the incoming ligand and on the concentration of the complex. So if you increase the concentration of the incoming ligand, you're going to increase the rate. Now, let's think about how that might be the same or different for a dissociative mechanism. So a dissociative mechanism also has two steps, but this time the complex first dissociates and then the new ligand comes in. We can do the same trick where we are going to label the forward and reverse rate constants as K1 and the second step as K2. And we're going to start with the idea that the second step is the slow step. Okay, so we're going to do the same thing where we write the rate law based on the slow step. So rate equals K2 times the concentration of the 5-coordinate intermediate ML5 times the concentration of the incoming ligand. Now, ML5 is an intermediate, so we need to do the same steady state approximation to rearrange the rate law so that we can get it in terms of the starting complex, ML5X. And so the way that we're going to do that is set equal to 0 the rates of formation and decomposition of ML5. So the rate of formation of ML5, so K1 times ML5X, so the rate law for the forward reaction, minus the rate law for the reverse reaction in the first step, which will be ML5 times X, the leaving ligand, minus the decomposition of ML5 in the second step when it forms the complex with Y. Okay, so we've written the rate law based on sort of each of the steps, forward and back. We set all of that equal to 0 because we're saying that the concentration of ML5 is not changing, so the rate is 0. Okay, if we rearrange all of that, again, we're doing algebra to collect all the terms to show, to find the concentration of ML5, then it's going to equal K1 times our starting complex ML5X divided by K-1 times X plus K2 times Y. Okay, so we put this whole thing back, substitute back in for ML5, and when we do that, we get that our rate law for a dissociative mechanism is rate equals K1 times K2 times the starting complex ML5X times Y divided by K-1 times X plus K2 times Y. So we see that in our rate law we have the influence of both the incoming ligand Y and also the leaving ligand X. So if we think about kind of the extreme cases, so for example, if we consider the case where the concentration of the leaving ligand, there's a whole bunch of leaving ligand in the solution, and so that it is much, much greater than the concentration of the incoming ligand Y, then that will mean that those terms in the denominator, that the K1 times X, will be much, much faster than K2 times Y. So basically, if X gets really big, then it dominates the denominator of the rate law. And so if we do that, then that kind of changes the rate law. So basically, that means that the K2 times Y part sort of effectively becomes 0, and we can imagine that it goes away. And so we can rewrite the rate law as K1 times K2 times ML5X times Y divided by K-1 times X. Okay, so you'd get a rate law where you have K observed, so all those rate constants together, times the concentration of the starting complex times the incoming ligand divided by the concentration of X. So what this means is that the rate will get faster if you add more complex or more incoming ligand, but you can slow down the rate if you add a whole lot of the leaving ligand. That was not true in the associative mechanism. We didn't have any component, any influence of the leaving ligand in that rate law. We can also consider, if we back up a little bit, we can consider what happens if instead of adding a whole bunch of leaving ligand, what if we add a whole bunch of incoming ligand? Okay, if we do that, then in the denominator of the rate law, the K2Y term will dominate and will be much larger than the reverse term. Okay, so that basically the K1 minus X term will sort of functionally become 0, and we can think about how that will change the rate law. So if we do that, if the K negative 1 times X goes to 0, then we'll be able to cancel out the concentration of Y and the K2 in the numerator. So the rate will become K1 times ml5x. So at large concentrations of incoming ligand, the rate doesn't depend on the incoming ligand. Okay, so you can keep adding incoming ligand and the rate isn't going to be affected by that. So we see that you add you keep adding, and eventually the rate will saturate where it no longer depends on the concentration of Y. And so when we say saturate, what we mean is that we would expect that if we were to measure rate as a function of the concentration of the incoming ligand, that at low concentrations, we would expect it to keep going up based on the sort of full version of the rate law. But if you keep adding Y, if you really pack the solution with Y, then eventually it won't affect the rate anymore, and we'll see that the rate curve will saturate. So that's an experiment that we could do to see if the mechanism is associative or dissociative. For an interchange mechanism, there's only one step, so we know that that step is slow. We'll also call this rate constant K1. If we write the rate law based on this mechanism, we just get that we have K1 times ml5x times Y. So this reaction is second order in and first order in each of our components. And so if we were to measure this experimentally, we wouldn't know that it was K1. We would just get K observed times ml5x times Y. Okay, so we see that this is the same rate law as an associative mechanism. So it can be tricky to tell how the rate or what the mechanism is if you find out that your reaction is first order in both your starting complex and in your incoming ligand. But you can use this to distinguish between an associative mechanism and a dissociative mechanism, because as we saw before, a dissociative mechanism has a much more complex behavior based on the concentrations of the incoming ligand and the leaving ligand. So to put all that together, if we compare the rate laws of the three mechanisms, we see that an associative mechanism and an interchange mechanism are both second order, and so we would expect that behavior dependence on the concentration of the incoming ligand for either of those mechanisms. For a dissociative mechanism, we see different behavior. We see that the rate is inversely proportional to the concentration of the leaving ligand, and we also see that at really high concentrations of the incoming ligand, the rate saturates, meaning the rate no longer depends on the concentration of the incoming ligand.